Okay, so this was a suggestion from Steffi actually about because lots of people she told me are doing mostly depth profiling, especially now with the ROIS, and she thought it would be nice to, because I kind of covered this before in the kind of general overview of simsMVA and MVA, but she thought it would be nice to have some sessions focused on depth profiling. So I will start with this one. And if you haven't seen the ones, early in this year where I introduced MVA in general and then simsMVA, I will paste the links maybe after this to the recordings, because most of the things here will not be covering today, so you may not be familiar with the terms, but hopefully it will be useful for everyone. So depth profiling, and I don't know if you've seen in the team, I left this image of a depth profile. So some of you have seen this before. So basically, as you may know, I work with interfaces. So this is a really nice example of looking at an interface. So you can see all the features you get from depth profile. So you have like the first compound, and then you reach the interface region, you have the dominance of a second compound, and then the kind of substrate signal. And all these oscillations, they may be related to, it can be some periodicity in the samples. I work with 3D printed samples. Sometimes you have this kind of layered structure that is reflected in your depth profile. Well, other times it's just an artifact from topographical, highly topographical surfaces. So if it's a really rough top surface, you end up with this kind of artifact, with these oscillating patterns across the whole profile. But in fact, this is it's not really a depth profile. This is from back in the days where we still the beginning of the pandemic. I was searching for kind of I was doing this Google search to see the interest of what people were searching mostly over this year. So you can see people looking for restaurants before March was much higher than bread recipes or toilet rolls. And then we have this interface, which is the toilet rolls. And then people just lost interest and started to search more for bread recipes. I don't know how it's looking like now. Maybe we have restaurants back up again. So this is just April, right when we started the lockdown. So to me, it was interesting because it looks exactly like a depth profile, even with the artifacts, as I said. So the artifacts here are actually kind of weekends, it peaks on weekends because people tend to go out or, cook at home. So yes, you can see we have all the similarities. So depth profile is just kind of a time series of, any time series will have lots of similarities with depth profiles. So if you were here last time I presented, I was talking about ROIS matrix augmentation. I will not go on about this again, but just as a recap, as we were saying is we can, in a data set, before we do any kind of statistical analysis, we can include more data from related samples and create a single matrix with all these things together. So basically, we're just augmenting the matrix. So we're keeping the same set of variables. So in this case here, all the same peaks in tof-sims. So I gave some examples of like this one that we published. For example, we had different treatment times and we had mapping data sets for each of these samples treated at different times. And we merged everything together and processed to find a consistent set of solutions that would describe the chemistry of the surface. So basically, I want to explore this idea now with depth profiles. It's actually much simpler because we don't have the pixels, we don't have to restructure the data. It's just a sequence of points, like a time series that we can just combine it from various samples. So yeah, so I want to use this concept to process multiple depth profiles. And then I will try to show you how to export profiles consistently from Surface Lab. I will show you how to load all these profiles into simsMVA and give some tips on how to process and interpret. And before I start doing the kind of the practical bits, I will just cover the two examples I want to show. So the first one is when we have multiple samples. So for example, in this case here, you can apply to, most of your many of your cases or samples will, in my case here, I had several samples with different polymer formulations, so they're very similar, but there's small tweak in the concentrations of the polymers used to make them. And then the gold nanoparticles were deposited on each of those samples, and we depth profiled all of them. So we want to compare them all together, and we want to do MVA in a consistent way so that we can compare all these samples. So this is the first one, so basically multiple samples. And the second one is in a case where we have a single sample. So this is a part of collaboration with Viren. I don't know if he's here today, but basically this is a worm, and where we have a full 3D data set from depth profile. And what we want to do is the profiles at different areas, or what we call like ROIS, regions of interest. So you want to compare the profile here on this end, let's say the head, a profile here around the tail, center, and also the substrate. So we can, pull 4 depth profiles or even more and compare. So I want to show how to do this and how to process in simsMVA. So yeah, these are the slides. So from this point, I'll kind of do a practical demonstration. So if you have questions, just stop me. It's even, I think it would be nice if you have questions actually, because it's a bit strange to do these practical demonstrations without anyone giving feedback. So yeah, just feel free to either type in a text or whenever you read, or just say something, just interrupt me, it's fine. Okay, so the first one, as I said, I had several samples, and I wanted to. My Teams thing is flashing here. Do you have a question? No. So the workflow, basically, I have several measurements. So each of those here are a separate depth profile. So I won't be covering much of this today, but basically you have to make a peak list, right? So assuming that you know how to do this, otherwise we'll just leave the links for the other workshops where we cover this. But the quickest way, so without going too much into detail, to make kind of a pick list that will have the areas of interest of all your data sets, it's to have an overlay. So I'm just clicking and pressing V to enable them in the overlay. And then I will click in the main window and press Z to overlay. So you can see everything is overlaid. So I can use this view to create a pick list and make sure I'm not missing anything. Some peaks may appear only for one specific sample. So if I make the pick list based in only one of them, I may miss important peaks. Right, so just skipping ahead. So once you have a full pick list, what you can do is apply it to the others. So and in Surface Lab 7, by just having the list, you also, if you go to the profiles software, you have all the peaks already there. You don't need to reconstruct anything. So what we can do then before we export the data is just apply it to all the others. So you may be familiar with this. So for example, on this left-hand side panel, I click on the target. I double click into one, I have a pick list, then I just click once to highlight the target data set I want to apply the pick list to. Then I come back here in the pick list, right click in the pick list, and go replace all existing pick lists of selected spectra. So when I do this and go to the target one and then double click to actually open it, you will see that I have the exact same pick list there now. And this is important, right? Because we want to process them all together, so they need to have the exact same pick list in order to be part of the same data matrix. So there's an even quicker way. You don't have to do one by one. So if you hold Control and highlight all the ones you want to apply the pick list, do the same, right click, replace all existing peak lists of selected spectra. And then there you have this list now. And if you go to the profiles software, you can see the same set of profiles, which is coming from your peak list. So now, so obviously I skipped all the part where we carefully select the peak. So do a peak search or things like this, because we already talked about this before. So I just don't want to waste time today on this. So once you have this, you just need to export. So the quickest way, like in this case, because these are separate data sets, you have to export one by one. So you just go File, in the dev profiles software, you go File, Export. And then you can either keep the same name or just give any name you want, because if you create a text file, a txt file with the data, so just make a separate folder here. So when you click Save, this window will pop up asking some details. So basically, if you keep all the ions in the view here, apart from the total, yeah, let me go just back. I will cancel this. So here in the list, you can take which ones you want to see, right? So if you keep all of them there, apart from the total, it's the simplest way to export, because it means that they're all here, they're all shown here, and you're not doing any extra processing such as normalization or smoothing. So you go export, save, and then you don't have to worry about any of these parameters. You just go use display configuration, and then you press OK. So let's go to the folder. So yeah, so you created this file, which is 80 kilobytes. So we have to do this for each of the dev profiles of interest that you apply the same peak list. So now I will do it for another one. So like this one. So double click, open it. It's because I already applied the pick list just now in the Spectra software. I just have to go File, Export, and then Save, use display configuration. Another one, double click. You have the profile, go File, Export, Save. Yeah, guess you get the idea. So I think I have 7 or something like this, so I won't be doing all of them because I already did it before. But yeah, that's how you do it. So now we need to go to simsMVA. Again, if you're not familiar, I will paste a link after on an introduction to simsMVA. So we go and create a new tab, new profiles tab. So we can, example 1. So as you may remember that the first button here is to load. So you create a tab, it will be empty. So you click load, and then you go load file, and you go and find the files you want to load. So these are the ones here. So you see 1, 2, 3, 4, 5, 6, 7. Yeah. So you can hold Control, hold Shift. So basically, you can multi-select, right? So I'm selecting all of them in one go, and I go Open. And then you ask kind of, please select type of data. Go Surface Lab 7, which is the one we're using. And then it creates this huge profile, which is basically one profile stitched to the other. So when the first one finishes, the second one starts. If you click split, it will show you them in the split view. But basically, they are now part of a single matrix. So as I said, we covered this with gold nanoparticles, right? So let's look at the gold. Is that? Yeah. If you look at the gold ion profile, you can see like the first sample actually didn't have any gold. So you can see, let's compare, let's remove that and put some polymer related peak. So yeah, you have in blue the polymer peak, and in red the gold related peak. So you can see it's very intense on the top surface, and it drops for each of the samples. Apart from this one where we didn't have any gold. And if you remove the split, now you can see the gold coming up and down. So obviously we know this is not a real sample, it's just a combination of all the profiles. So as long as you know what's going on, you can even use this kind of general view to understand. So I knew how much gold I used for each of those samples, or for how long I treated, or what was different in the polymer formulation that may enable more gold to be absorbed on the surface. So this already helps me to kind of see a pattern, you know, this one has more gold than all the others. So yeah, so you can use the split view or the non-split view, the together view. I've shown this before. This one here is a moving average function, but because the variation of gold is only in the first few levels, you create artifacts if you do that. You see, I'm starting to distort too much. So for this one specifically, I will not do any averaging. So another thing that's interesting to cover, especially when you're dealing with multiple profiles, you know, maybe even if you use the exact same settings, maybe things changed, and being current changed, or you archive for a bit longer per layer for one of the profiles. So you won't be exactly sure that these differences are actually because of chemical changes or concentrations rather than just acquisition time or things like this. So we can normalize everything by the sum of all peaks. So we will get the total intensity of the entire peak list and divide each peak by it. So you can see, so now for each level, all the ions intensity will add up to 100%. So you can see it kind of corrects for some features, right? So it's better to compare. Another useful one when you only have like 2-3 peaks of interest is to normalize by the sum of selected. So now it will normalize only by the ones that are shown here in the plot, the ones I selected. So basically, for each level, these have to add up to 100%, the blue and the red. So when you do this, you can see for the one without gold, you see that there was actually some gold there, because actually what happened here is the polymer formulation was not designed to hold on to gold, to have the absorption, but we still did the treatment as a control. So you can see there's some residual gold on the surface that you can see in the normalization, where it's much less, right? So the other ones are close to 100% on the top surface, and then it drops down. So this kind of normalization is very useful as well, especially when you're comparing. So in the split view, you can see for each level, it adds up to 100%. So you kind of ignore all the other peaks and only consider these ones. So if I add another one, just any other peak, we'll take that into the account for the percentage, right? You can see the red and blue now are kind of dominant towards the bulk, but the gold still very intense at the beginning. Right, so this is just kind of visualization of the data you have. So now, let's go back to normalize by sum of the entire list. So let's do, if you remember, NMF of this to see whether we can consistently find factors and members that will explain this data. So this is TOF data. So if you remember, we need to Poisson scale. And then I would just click the NMF button. And I don't remember now, but so let's say this one has 3 factors. So it's, if you remember, for imaging, it takes much longer to calculate NMF, because with depth profiles, you don't have, you know, the pixel dimension, like the second dimension, so it's much quicker. It's just the number of levels you have here. Right, so again, we don't have time to cover, you know, how this works. Hopefully you remember but very briefly, here on the top you have the peaks related to each of the end members. At the bottom you have the profiles. So because we have this joint data set, I think it's very useful to kind of just click this button to create a separate window so you can resize it and see in more detail. So if we put them all together, you can see that it's nice. I mean, we know these samples are all similar, so we can see that you found the blue, which is very likely related to all the gold peaks. So we go here like number 1. You can see if you look at the numbers in the masters and go back to the software to check, these are all the gold and actually gold sulfur related peaks dominating this end member. And the other ones are related to the polymers, and then we will need some interpretation to see what's happened, because as I said, we changed the polymer formulation for each of those samples, and it's likely that the red, so number 2 and 3, are actually related to this kind of change in chemistry. So it's basically a mixture of 2 monomers, and so it may be related to the presence of those 2 monomers in each case. And remember, I just said we can normalize things by the total. Right now we have 3, and we can do exactly the same sort of normalization. So for each level, we'll be adding up to 100%. So, and again, you can use the split, just like we had before, and it separates all the profiles. So quick interpretation here, as you can see, the yellow is likely to be the monomer that will not have this binding with gold, and red is the one that actually interacts with gold because it's present in all the samples with gold. And then you can see how much gold you had on the top surface for each of them, and if you had more things changing or more complex things, it could have been picked up here in a very consistent way because we processed them together. So we have 3 colors to describe the chemistry of all your profiles. So it's interconnected, right? If you were to process each of those separately, you know that NMF is not always the same solution, so you will need to check, and you wouldn't be 100% sure that the solutions are consistent. So here, obviously, if I run again, it may be a slightly different solution, but at least for this run, I know it's the same solution for all the profiles. So I think this is very powerful, especially when you have several samples and you want to compare things. So it helps on giving you the confidence on your assignments afterwards. You know, you for each of these colors, you know the ions, so you can go back to them and make assignments based on their correlations. And also helps on visualization, like presenting this data in this way is much clearer than just trying to show the processing of each of those separately. And also you can do some more post-processing. You know, you can just do extra normalization and work out the relative amount of gold on the surface from each of those, but not only using kind of the gold minus peak, but using the signal that was picked up from the analysis that takes into account all the gold peaks. So yeah, to me, that's very useful. So I hope you can see how you could use this to some of your data sets as well. Right, so yeah, this is the first example I wanted to show. So before I go to the second one, I will just, as always, just leave maybe 5 to 10 seconds for questions if you have any.
There are no questions in the chat. I could have a bunch of questions, but I can wait until the end, maybe, because maybe you're going to talk about them anyway. So, yeah.
Well, if you want to ask one of them, it's fine.
Okay, I was just wondering, so when you first, if you go back to example, to the data, to the top where you have the data, so when you went to start the NMF because it's a TOF, it's TOF data, then you went to NMF and then Poisson. You chose one of 3 options, and I was wondering whether if I was dealing with algorithm, and you chose So I was wondering whether if I'm doing ORBI profiles, what would you choose then? Because I guess we shouldn't be using the Poisson scaling.
So Yeah, that's tricky because yeah, you wouldn't necessarily choose Poisson scale. You could do the normal one, which is quicker, and even the alternating least squares, because there's no justification for using the Poisson for Orbi, right? I use Poisson for TOF because it's, you know, it's proven that is the most appropriate for TOF data. For Orbi data, it's something we discussed before. There's no appropriate algorithm so far. So basically, for Poisson, I confirmed this like during my PhD. I did some very systematic testing. There are several papers that show this is more appropriate for TOF data, but for Orbi data, we don't know. So you can try, you know, you can even try all of them and see how it compares, because we won't have any justification for using these algorithms. So yeah, not necessarily Poisson, but doesn't mean you couldn't try for Orbi.
Okay, cool. But you will recommend the normal one then?
Yeah.
Okay.
Yeah.
Thank you.
Right. So let's do the second one now. So now we go, so we go back here, and as I said, it was this image 3D data set of the worm. So now, as I say, obviously we could exploit this in 3D like we did before, right? We could process every single voxel, which is a huge data set, and it's full of noise as well because the counts per pixel, it's not very intense. So one alternative way is to create, as I say, regions of interest, pull the profiles in those regions, and do this kind of consistent processing of all these profiles. So the first part that you may be familiar with is the creation of the regions of interest. So in the imaging dataset software, you go analysis, ROI editor, and oh yes, so let's go back one step. So before we do this, obviously you need to have your pick list applied to the data, right? So now, again, all those steps of what's creating the pick list. And here you don't have to use the overlay thing because you can just use the total spectrum of your entire 3D data set to create the pick list. So once you have it, you go then to the imaging software, analysis, ROI editor. So ROI stands for region of interest. And then here on the right, you have this subset that says image sources. You click there, and then you can use any of your ions as a guide, you know, to find what's the region of interest. So let's use the total ion, right? So this is the total image. So you go back to the ROI list tab, and I already have them here, so let me just delete them all. Right, so you click no, and then you can use any of those creation modes here. You may know how to do this already, but anyway. So if I do, let's say, the center square, I can select specific size, then go add, and it creates this blue square that I can move. So I will say I want this one here, so it will be, I think that was too large. Let's remove it. Let's do it again. New center square, just a bit smaller. Bear in mind, if you make a very small one, it will be very noisy because you just gain a signal from few pixels. Okay, so I'll move it to here. So this is my first region of interest, and then I can just now create all the ones I want. So because we want to compare them in a consistent way, I recommend creating exact copies of the ROIs in terms of the size, pixel size, because we can normalize later. So you could make a huge square for the substrate and then just normalize, but then you'll be having kind of different levels of noise, and this may interfere with your analysis. So I think it's best to just click duplicate. Now I created a green one. So you click there, you will see the green. You can click and drag it. So the green will come here at the bottom. So the blue there on top, the green at the bottom. Then I can duplicate the green, creates a red one, move to the center, and I will create another one in light blue and move anywhere around the substrate. So I have 4 regions of interest. I could have more, right? So just go OK. And now we move to the profiles because we're only looking at depth profiles. So we move, as I said, this is a 3D data set. So we have depth information. So you see all the ions applied in as we had for the other ones. So, but before we do the export, you come here at the top, you have all these drop-down menus. One of them, it says total area. You click there, and you see all the lists, the list of regions of interest you just created. So I will go ROI1. You can see here on the bottom right that it shows a tiny square that we created. And then you saw, right, it takes a while to update. So the larger your data set is, the longer it will take, and then the larger the pick list as well, the longer it will take. So sometimes it even crashes, so just be aware of this. So now it's just showing the profile. It's showing the profile only for the region. So I'm ready to export. So I go, as we just did for the other example, we go File, Export, and any name you want. And then you can just say, because now you need to give an extra name because they're all coming from the same data set. So you can say like ROI1, for example, or any file. I could say head or tail or something like this. And again, if you do the thing I said, you just keep all the ions there. You can just use display configuration, and it will create a file for you. So now for the next one, you just click there again, and then move on to the next region of interest. And then again, it will take a few seconds to minutes for it to update. So once it's updated, you can do exactly the same, export. And then I will call it ROI2, save it. Okay. And then we go and do it for as many regions of interest as we're interested in. So we have 2 more, but I've done this before, so we just load it from simsMVA. So basically we end up with 4 files in here, right? So if you create more, you can have 5, 6, 7, etc. And as I said, they don't necessarily have to have the same area, like this square here. They're all the same size, but it doesn't have to be like this. You can make bigger ones, but just you have in mind that you may have different levels of noise for each of the data sets. Right, so we go back to simsMVA, create profiles tab. And then do exactly the same, but from this point, we're just doing exactly as we did before. Load file. And I have these 4 files. Then it created this kind of joint profile. As you can see, the for these ions specifically, is very different because we know it's the only one outside of the worm. And again, we can use the splitting to compare all the kinds of normalization. Well, you only have 1 if you normalize, but some you create those artifacts when it goes to 0. So I said I wasn't going to do moving average for the other one. But for this one, you can see it's very dense. It's lots of points, so we can do a little bit. You see, kind of smooth the data, but never do it too much. So it depends on the size of the data set. If you do too much, it will look nice and smooth, but it creates all kinds of artifacts that are not real features of your data. So just do a little bit. Right. So I would do NMF again. So I will pause on scale. for this one, it works. I can either normalize by the same as did before, or just leave it as is, because now the difference is these are not different data sets. It's coming exactly from the same data set. So as long as I use the same area, like the squares, you know, it's the same level of noise, presumably, the same kind of counts per second and all these things. So it's already comparable. You don't necessarily have to normalize. If you use larger square areas for one of the ROIs, then you have to normalize. Otherwise, you know, for all the ions will be much more intense for one of them just because the area was larger. So in this case here, we could try both. We could try with and without normalization. So just to show you, we'll do it without. So again, we'll do that. So I think I have some tests I did before. It would be nice to have a discussion. So let's see if we can show you something. Yeah, so while we wait, I will just show something that I think it's useful, especially when you need to export. If you're here and you want to update your peak list, so I want to include the hydrogen peak, for example. You can go click there, and then as you do, just click add peak. Right, where you see you will go to the end. Where is it? Yeah. So the number of the peak in your list will be in the end. So, and we used to having these lists ordered by mass, right? So, and when you actually export this to simsMVA or load into simsMVA, it's a bit confusing because of the way I coded it. It will not reorder. So I need to update this, but right now it's a handy tool we have here in the Surface Lab is you can order, like you want to order by area, you can click there, or you can order by mass, which is the one we're used to. And then you have this button here which says reorder IDs. So when you click there, it reorders it. So now the hydrogen peak is the first one. So number 2, because 1 is the total. So yeah, that's useful. So just let's see if it's done. Yeah. Right, so again, here you have all the ions related to each of those end members. And then we can make this bigger and have a comparison. Okay, so we'll do some renormalization just to help on the visualization. So add up to 100% at each level. And you can see first yellow is clearly the substrate signal, something that the worm was on top, right? Because it starts very intense and it stays very intense for the ROI on the substrate. So this helps us to imagine that you hadn't gone through, because here we've gone through the entire sample. So we can see the yellow coming up after we etched everything. Like it could have been that we stopped here. So we're not sure if we're setting the substrate. So this is a very quick way to, get all the ions related to the substrate because you have one of the ROIs as your substrate. So the other 3 are different parts of the worm, right? So the interpretation is tricky. So this is much more complex data set than the previous one. So all these changes could be because of just the morphology, or it could be actual chemical changes. So let's say if I added a 5th component here, maybe only the center of the worm would have this because it's related to the biology of it. So it's, some chemistry that's only present there. But in this case here, you can see all the peaks across all parts. The blue stuff, you can see it's covering basically the worm because it drops very quickly, and then you have this inside part. And I think the most interesting is in the second one, which I think was the bottom part. This red signal is much more intense. So to check whether this is actual chemistry or some artifact of the solution, you need to go to the peaks, right? So it's related to it. and then go back to your original data and check each of those peaks to see whether they make sense in terms of the chemical assignment and the distribution and all these things. But this kind of analysis gives you a really nice indication and also a really good guide for what to look for. Another interesting thing is that you can see that yellow doesn't take over for the first one, like for the others. So is it because that part is thicker, so it didn't etch through? Or is it because the etching was preferentially in one of the areas? So, you know, you need to have these things in mind to help your interpretation. But if everything was really well controlled, you could say, oh, actually this bit was thicker. So, you know, it gives you some information on the layer thickness of what you're looking at, only by, you know, looking at the yellow signal that's not taking over. So you still have some dominance of the purple, which we know is related to the insides of the organism, and so on. You know, it is a very complex data set. So, and that's why it's a very useful tool to use, this kind of consistent processing to help you understanding, because you have so many peaks, you don't know which ones are related. So once you do this, you can go back and start looking at the chemistry. And obviously, with this is tough data. With Orbi data, it's even more complex, right? You have so many peaks and this huge dynamic range, so you don't know which ones are the actually relevant ones for you. So once you do this kind of analysis, it may help you to go back and look at the things of relevance for you. Okay, so yeah, that's it. These are the examples I wanted to show. I hope it was useful. And if you have any questions, yeah, or want to discuss anything, we still have some time.
Thanks, Gus. That was awesome. There are still no questions in the chat. You kind of answered my question that I had. So I was wondering, so you answered it with the last example and the substrate, because I was wondering, it's at the beginning you compared it to the workshop that you did in September about the image stitching, right? So it's kind of like stitching of depth profiles. And I was wondering whether if you have a bunch of reference samples and you stitch them with your actual samples, can you this way track where in the complex sample your reference materials are? Would that work this way? I guess this last example with the substrate looks like.
Yeah, it's well, that's interesting because it's kind of a combination, right? Because you don't necessarily have to profile the standard, right? You could have just a surface map of the standard and then add this. So definitely it will work. So
yeah, but in Orbi, for example, we don't do the images, we just have the depth profiles, right?
Yeah, so even if you don't etch, you know, as long as you know what you're doing, like, you know, I could stitch to the end of this data here, kind of a data set of a standard scan by scan. So it will be constant, right? It will just be the same.
Yeah.
And you can kind of judge as a fake profile, which is not showing any etching or anything, but it's being added to your matrix to, you know, to help you find solutions. So obviously it's not designed for this, it's designed for like comparing profiles. So basically you're just adding repeat rows in the matrix, but still it helps in the statistics, right? Because each scan will be slightly different, so you have this variation. So yeah, I think it's a really good idea. You know, if you have like the measurement of a standard, you just exports all the you go to the profiles software and then export it as a profile, even though there won't be any changes because it's not etching. You can use it as a kind of a fake profile, or as a, you know, steady still profile, something like this.
Okay, that's cool. That's very useful. Thank you. Any other questions?
Hi, Gus. Hey, Gus.
Hey.
Could you briefly go over how you do these etching TOF images?
Image sensor, the experiment.
Is it like as in, how do you do it on the Surface Labs, like when you're acquiring the data?
You mean a 3D data set?
Yeah. How do you get a 3D image data set? So
I don't have, you know, here we need the kind of the version where you can start measurements, but basically when you go start measurement, you have like the 2D on the left on the panel, and then you have 2D large area, and the third one is 3D. And then in the 3D, you can set both the kind of the etching parameters and etc., and also the imaging parameters. So in essence, every data set you acquire with TOF will be 3D because it's always rastering the beam. So this information is recorded every time. So as long as you raster with a reasonable pixel size and area that will give you spatial features, in the end, what you have is if you open each of those softwares like the profiling, the imaging, and the spectra, the information is there. So if you open any of your TOF datasets and go to the imaging software, go 3D reconstruction, you can load anything. You can see that it's actually 3D. So sometimes the region is so small and the pixel size is so big that there's no actually information in the XY dimensions, even though the data is structured like this. So the data is always structured in 3D for TOF data. Now with Orbi, it's a bit different because the way the software records, if in one of the modes, even though it will raster the beam, it doesn't record it as a 3D data set. So you have to specifically, I think so far with the Orbi, I think you have to do like an imaging data set with Orbi and do it for very long so that it's each scan represents a different depth, because as you remove the material with the argon, you're also kind of etching through, right? So you have to do it for very long, and then it's kind of a 3D version of the Orbi. So it's not like automatically structured as far as I know, because here is dual beam, right? So one of them is the beam is just imaging and acquiring data, the other beam is etching. With Orbi, most of the times what we do is we use a single beam to acquire and etch the material. So yeah, so it's basically it's always 3D as long as you're doing with the TOF.
Okay, thank you.
Let's stop sharing this. Am I still sharing the screen? I'm not sharing the screen anymore, am I?
No, you're not.
Okay. So yeah, do we have any other questions? Okay, if not, we just finished now. As I said, I will just leave the links here for the previous workshops, because I understand I referred to many things I talked about before, and I'm not sure if everyone saw the previous workshops. So if you are interested in what's being presented today, it may be worth checking the previous one. So I will just leave the links. And Steph is not here, right? No. Okay. So as I say, you can write to Steph if you had concerns with regards to Sims or any issues. And yeah, from my side, that's it. If there's no more questions, we can finish now.
Okay, thanks, Gus. That was great.
All right. Thank you. Thank you, everyone. See you next time.
Thank you.
See you. Bye.
Thanks a lot.
Bye.
Bye-bye.